Is today just general review?
Yeah, that's the goal for today. We completed all of our work in 6.3 last time. So we're pretty much just going to go through the problems on this file here for review, or whichever questions folks might have as well.
Sounds good, thank you.
Yep, absolutely. And we're nearly there. It is, yeah. All these problems are new and fresh. They even had some pretty good hints at the very end. But looks like it's time to get started. Welcome back, folks. Any other questions at the moment before we begin? Okay, well, I have a couple versions of the sample final exam problems, versions 1, versions 2. You've seen a lot of these problems before. This is just really the full set of all those problems. Forget exactly how this goes. One of them is the lecture notes. Let's see here if I can tell. Yeah, this one looks like the lecture notes. So if you want to go back to the lecture notes, there's blank ones on the top of Canvas. But this is one gigantic file of the problems that we did in class that are suitable for the final exam. So some of the problems are actually deleted off here since they're more just discussion kind of problems. This one has brand new problems going all the way to section 6.4, although that's not going to be officially an exam question, just an extra credit question. And this one has some brand new fresh problems that we'll be taking a look at today. So that's our goal, just to start reviewing for the final exam. It's going to be hard to review everything on this document in one day, but I'm going to go back and complete all the solutions that are in here and get them uploaded probably sometime on Friday. Well, I don't have a ton of announcements. As far as the final exam, it's going to be on official day, Friday. If you're in the online section, it can be scheduled for any time on Friday. And if Friday just doesn't look like it's a good day for you, it's a weird day for Tuesday, Thursday class, you can take it earlier in the week if you'd like. For the in-person section, it's from 10 a.m. to noon, 12 p.m. And we had to get some corrections on that in several places. It'll just be in the classroom, CHE 215, just like the other exams. Well, I think that's pretty much it for the announcements. Just a reminder that for studying for the final exam, it's a good idea to have this sheet pulled up, the formula sheet, since this is going to be the real last page of the final exam. Also, there's extra credit opportunities relative to the final exam that we discussed. Homework sets are a huge extra credit opportunity. And one thing that we mentioned once on the syllabus is at the end of the semester, I am going to drop your lowest two homework scores from the homework set. But any homework you can get in by Friday, the last day, the cutoff date, can improve your grade a lot because homework is worth more than a single exam amongst exams 1, 2, and 3. It's worth as much as the final exam in this course. It's kind of just like an encouragement to get through those sets. It's the best way to really learn this content. So getting caught up on your homework is probably the number one recommended strategy for preparing for the final exam. If you're already caught up, then that'd be a good time to turn over to looking into these additional problems. Version 2 are the new ones. Version 1 is lecture notes that we've solved before, or take a look into these problems once again. So here's where the document starts. Just a long list of problems, but I want to focus on the very bottom just as a reminder. There's two sections that we don't have official homework for this course because I think it's a bad idea to try to collect homework on finals week itself. That was sections 6.2 orthogonal sets and 6.3 orthogonal projections. And if you look in those notes, there's some really big hints on what will be good exam questions you should really expect on the final exam. And it's the same as these last two questions as well. Problem number 17, just a different scenario, maybe a different vector space, maybe R4, for example. Or question number 16, I had to put an edit on this. I forgot to say what you're plotting. It's the stuff in red. These are two questions that are actually on the final exam itself. Because there was no homework for 6.2, 6.3, I felt like this is more of a sake of fairness. Also, I think it makes sense to just start here. Does that make sense to folks? Should we start here, then maybe wrap back to the top? Okay, let's start here, see how bad these numbers might get. And then we'll just go at the very top of the notes looking into the start of the semester and work our way down. And if you have any questions that come up, maybe a different problem from anywhere else, old exams, homeworks, and so on, don't hesitate to interject. I'll be happy to discuss them. So let's start off with this one. This one's a challenging exam problem on the final exam, even after usually giving that hint year after year, because it forces us to really visualize what all these objects are going to look like geometrically. So we have a subspace W, which is the span of one single vector, 4, 1. We have another vector, 2, 5. And we know from the orthogonal decomposition theorem, we can represent Y in this way. The projection onto W and the component of Y orthogonal to W. So we want to sketch all of these objects, every one of these components, the vector U, the subspace W, the projection, the component that's orthogonal, and the orthogonal complement of W. Here's how it all comes together. I wrote the same statement here. You don't actually have to compute Y hat and Z on this problem, but if you have additional time at the end of the exam, it's a good check to see if everything looks about right. This is graded on partial credit, and if things are in just the right neighborhood, then it's good enough for me. I'll actually give you some grid lines on paper here. First thing I would plot is U. In fact, this is kind of presented in a way that's sort of sensible for the order to plot. U is the vector 4, 1, so it's right here. Then next thing is the subspace W. W is the span of U. So it's going to look like this. The span is also a subspace, so it has to contain the 0 vector. And I don't know why, these lines are tough to draw when they have kind of a small slope. But there it is, the subspace W. So getting Y hat, we can't do that directly just yet. We want to first plot the vector Y, and then we can see what the orthogonal projection Y hat would look like on the graph. So Y is at 2, 5, so we're going to go up 1, 2, 3, 4, 5. We're about here. Picture can look a little bit odd if my spacing here isn't uniform, and it doesn't look completely uniform. But let's just go with it. We'll use our imagination to try it the best we can in visualizing where Y hat should be. So if this is Y, Y hat, being the orthogonal projection, is a point somewhere in the subspace W that has the minimal distance. So there's some vector here that's closest to the vector Y. That's our best approximation theorem in section 6.3. It would be about here. Again, it's not perfect since I'm not plotting my tick marks perfectly on the x1, x2 axis. But here's the thought. Orthogonal projection means whatever vector is here, this is the one we call Y hat, has to make a 90 degree with the vector, say, Y and U have to make 90 degrees. And the vector Y hat is the one in the subspace that connects back to Y in this way. So after we have that vector Y hat down here, we can plot Z. Any questions at the moment with the sketch so far? Okay, so here's where Z connects. Imagine that there's this line that goes kind of like this. Except the vector Z really gets visualized this way. We just slide this down until we start at the origin, terminate here, and that's Z itself. It's the component of Y that's orthogonal to W, so it still makes a 90 degree angle in this way. And if we draw an entire line segment going out this way, this is the orthogonal complement, W perp, which is just the span of Z. So that gets both of them in one shot. So practice that out a couple times and see how it all kind of connects together. And it's not too bad of a sketch to draw. It's really surprising if you're asked to do this and you had no idea it's coming up, making it a really rough final exam question if it's a surprise. Any questions at all, folks, completing the sketch for this scenario? Okay, and sometimes people as a check do compute Y hat and Z in this problem. Reason I didn't ask you to do it on this one, on the real final exam, is This is more just knowing what things look like, your mental picture for these different subspaces and vectors. And also it'd be kind of redundant because exercise 17 is going to ask you to compute y hat and z, but just in a higher dimensional situation. Dimension 2 this time for our subspace W. First, we are hoping that this is a basis. It does half the work when we have it spanning to result in W. Looks like it's also linearly independent, but we want even more. For this to work out for us in part B, we need an orthogonal basis. So that's what part A is all about. It's actually a really fast check here. I don't know why there's so much white space. We take u1 dot u2. We have to check that these vectors are orthogonal to each other, so the dot product has to come out as 0. Multiplying, we get 3 minus 2 minus 1 equals 0, and so that's some fast algebra there. This immediately implies u1, u2 it's definitely an orthogonal set because it doesn't contain the 0 vector. It's also an orthogonal basis for W. So let's just say is an orthogonal basis. So that finishes off part A. It's kind of like the freebie part of the whole question. And this is the gnarly computation part. I practiced this today just to make sure I personally could get through the numbers. They're a little bit rough on this, but on the real exam, I made the numbers a little bit more friendly. So pretending this is a real final exam, where you probably want to scroll down to is this, the orthogonal decomposition theorem. So this is what the whole problem is really all about. And we compute these little chunks to get y hat. This is the first main part of the problem. There's only 2 vectors, u1, u2 in this problem. So we just need this much of the formula. Let's copy pretty much this whole line in. You have to have an orthogonal basis to use this theorem, but that's what part A was checking for us. So that's pretty much going to give us the main formulas for the whole problem. The distance is just going to be the length or norm of that vector z once we get to it. So start off with y hat. Let's do the scalar portions first. Y dot u1 over u1 dot u1. So here's the vector y. So focus on this one and do the dot product connecting here for the numerator. We get 1 plus 2 plus 6. Now u1 dot u1 is going to be the sum of those components squared. So 1 plus 4 plus 1. So altogether we get 9/6, or these are good problems to reduce when you can. This will be 3/2. So we have the coefficient that goes here. Do it again for this portion to get the next coefficient. Y dot u2 over u2 dot u2. So now same vector y, do the dot product with u2 way up here. And we will get 3 minus 1 minus 6. Denominator is u2 dot u2, so that's 9 plus 1 plus 1. So this time we have -4/11ths, and that's the 11ths that makes the numbers not very friendly on this particular problem, but we'll get through it. If we did the easier problem and I gave you the harder one on the exam, that would be the worst situation. So these numbers are worse than what's going to happen on the real exam. With those two scalars found, 3/2, -4/11ths, we're just going to take this stuff, plug it in here and here, and this allows us to compute the vector y hat. So y hat is 3/2 u1 plus, or rather -4/11ths u2. And there's lots of ways to do this kind of arithmetic. Sometimes it's convenient to get the least common denominator right here and then just deal with scalar multiplications of ordinary integers rather than fractions. So if you go that route, it eliminates the fraction arithmetic or reduces it. We'll multiply this by 11 over 11 to get 33. 22 u1. Multiply this by 2 over 2 to get -8 over 22 times u2. Then we could factor out 1 over 22. So this is the nasty part of the whole problem. And take 33 times u1 minus 8 times u2. I forgot to load a calculator. We'll be doing that shortly. Don't forget your calculator as well on the real final exam for occurrences where the numbers are just not as friendly as normal. So 33 scaling u1 gives us 33. Getting mixed up on my brackets here. Let me put a parenthesis. So now that looks like a bracket for a vector. So I have 33 and then 66, 33. I'll go plus and scale u2 by -8. So this is -24. +8, +8. So now this is to wrap around 1 over 22, rescaling. 33 minus 24 will give us a value 9. Then 74, 41. These are divided by 22, so 9 over 22, 74 over 22, 41 over 22. This one reduces, but I'm just going to keep it all over 22 because the next step is to do y minus y hat. I'll just put that vector y into a denominator of 22 as well on the next step. But hey, we're getting there. That's our y hats so far. Any questions at the moment, folks, getting to that step? Okay, so next thing we're doing, finding that vector z. Z is going to be the original vector y minus y hat. So let's put this in a denominator with 22. So this is 22 over 22. 22 over 22, and then that's kind of inconvenient. So 6 times 20 is 120, carry in the 12, looks like 132, 20 seconds, minus, here's the y hat vector, 9 over 22, 74 over 22, 41 over 22. Okay, let me know if you detect any weird numerical anomalies. On the first subtraction, it looks like it'll be 13 over 22. This one's going to come out negative 52 over 22. And this is getting inconvenient. 132 minus 41. Well, if we subtracted 32, we'd have 100. And that means I need to subtract 9 more. I think that's 91 over 22, but I think this is a good time to reach for a calculator just to be sure on this. Let me know if you spot any numerical issues so far. (132) minus 41 somehow breaks my brain a little bit, but hey, it worked out. It's 91. So we have to take the length of this, but there's a really great supporting theorem in doing that. If you take out the denominator, factor out to 1 over 22, finding the length is easier. And another thing that I didn't notice at first, but upon closer inspection is you can also factor out 13. Divides evenly, 4 and 7. So let's factor out 13 20-seconds on this whole thing. 13 20-seconds leaves behind 1, -4, and 7. Let me double check the numbers. Yeah, with a negative sign as well. It's a good point to double check. Is this right? If we take z dot u1, the 13 20-seconds isn't going to mess up the dot product. It just multiplies the result of the dot product. So let's take this dot product that and see if we get 0. That'll be a 1 minus 8. So we're at -7. Plus 7 balances at 0. So these two vectors are orthogonal. Well, the gold standard is to check one more time. Z dot product u2 is going to be 3 plus 4, so we're at 7, minus 7 back to 0. So it really is orthogonal to this entire space W. It's in orthogonal complement in fact. So last thing to get the distance, we're nearly there, is to do the following. Let's just reflect on what this looks like. To get the distance from a vector y to a subspace W, that's effectively what we're doing here. It's just higher dimension for W. You find the orthogonal complement z and just find the length of z. It's the bona fide distance y to the space W that we're looking for. So coming back to down here, we can conclude on this by saying distance from y to the subspace W is the length of z. That length's not too terrible to calculate because it'll be absolute value of that scalar. So that reduces the work in the square root enormously. Multiply by the square root of z dot z. So now just this part is left. 1 plus 16 plus 49. We get 13/22 square root 66. And 66 doesn't have a repeated factor, so hey, that's even simplified as a root. It's just kind of a nightmare in the middle. Sometimes the numbers do get nasty, and these problems are a little bit harder to rig. But this is like a worst case. The exam has friendlier numbers in this situation. We did it, folks. We found the distance from a random vector y to an entire two-dimensional subspace. And the rest of chapter 6 is just more of what good is this topic for? What are the applications? But since these are the very new topics, I don't have homework sets for them. The exam questions, like we mentioned, are going to be very similar to these here. The very last question is going to be a section 6.4 Gram-Schmidt orthogonalization problem. That's only if you have extra time on the exam. It's only for extra credit. Well, we're going to wrap around to the very top, look into the older, deeper concepts and questions from back in the day. Any last questions at all before we skipped back to the top? Okay, so here's the beginning of the actual review set. Problems here are mostly in order. They're slightly mixed up. And same with the final exam. It's pretty much in the order we covered in class. Some of the problems are a little bit mixed up. That was more just to make sure a longer problem fits in with a smaller problem, so there's space to write. I didn't try to intentionally mix things up. So here's a problem from way back in the day. We have two vectors. We want to know for what value of a parameter h is a third vector inside the span of the first two. And a good way to think about this problem is just write out what the span is in the first place. It's a set that goes x1 v1 plus x2 v2. So that's just a linear combination of the vectors such that x1, x2 are in R with no conditions. So now it's the set of all linear combinations. So for a vector y to be inside the span, it just means you can solve x1 v1 plus x2 v2 equals y. This is what it comes down to. Y is a linear combination of those vectors. But then solving this, it's just a vector equation which you could write as a matrix equation or system of equations. Either way you visualize it, you're just going to throw it into an augmented matrix in this kind of way. So 1, 0, -3, 0, 1, 5. Augment with the right-hand side of that vector equation, 1h1. So now we're just checking for consistency. So we just need to get this into echelon form. We don't need reduced row echelon for this process. So let's start by writing out the first two rows. Can triple row 1, add it to row 3 to get 0, 5, 4. And then it's almost in echelon form the moment we eliminate the 5 down below here. So let's copy in first two rows again. Multiply by -5, add to the row below, and we get 0, 0. And let me include a little bit extra space here. We're multiplying by -5, so this is going to turn into a -5h. So 4 minus 5h. And now it's in an echelon form. Everything now hinges on 4 minus 5h. If that's a pivot, the whole system is inconsistent, which means that vector equation has no solution, which then means y is not in the span set way up here. So the only way to make this be consistent is that has to be 0 exactly. So here's the last connecting thoughts. Y is in span v1, v2, if and only if, we'll just use the biconditional arrow for if and only if, h equals 4 fifths. Because if it's 4 fifths right here, we get 0 right in that position, making it consistent. Well, any last questions at all, folks, with that problem from way back in the day? I think this is like week 3 or week 2. Okay, let's try out another one. I think that's a good one to start with because span is oftentimes a pretty tricky concept in this course. And so it just forces us to really look into what's the span in the first place. This one is mostly just a concept question. I don't include a lot of these. They've been kind of sprinkled here and there between exams 1 and 3. Not too many though. And same for the final exam. There's not going to be tons of these, maybe 1 or 2 at maximum. So it's just true or false. We'll justify it, but in exam settings, I often say you don't have to justify, so these don't take so long. We're starting off with a matrix A of size 4 by 6, and it has 3 pivot columns. So one strategy we used anytime this occurred is just kind of visualize it. Give your eyes something to see. It's 4 by 6, which means 4 rows, 6 columns. And I guess that means there's 24 dots here. Let me fill these all in. These dots are meant to represent any number whatsoever. Next piece of information tells us it has 3 pivot columns. So I'll circle the pivots, which means that entry right there is non-zero, or it'll become non-zero once we do some row operations. I don't know exactly which columns are pivot columns, so I'm just going to pretend it's columns 1, 2, and 3. It won't change the analysis, but it has to be exactly 3, so visualize this way. Now we're just going through the true-false questions at this point. It says for true or false, the matrix equation AX equals B has a solution for every B in R4. What would you all say to that? Does this feel true or does it feel false?
False.
Yeah, good call, Brian. This one is absolutely false. The trouble is there's not a pivot in every row. The moment there is a pivot in every row, we can go back to, say, not the invertible matrix theorem because it's not square, but theorem 4 from chapter 1 tells us for each B in Rm, Ax equals B has a solution. These are logically equivalent. So that is true, part A, if and only if we have a pivot in every row. But we don't. We're deficient of pivots. So it's false. Let's put in a justification because there is not a pivot in every row. And there's also not a pivot in every column. So that's the trouble with linear independence. Independence has to deal with AX equals the 0 vector and whether we have non-trivial solutions or not. But there's 3 free variables here, so there's automatically non-trivial solutions, which means false. These would be linearly dependent. Let's write out AX equals a 0 vector has non-trivial solutions due to 3 free variables. So false on both of those accounts, just too few pivots in this matrix. Next, it asks true or false. The homogeneous equation has non-trivial solutions. You know, that's part B. If it feels like you're hallucinating, you answered the question already. That's just kind of the nature of linear algebra. You can address essentially the same concept by asking it lots of different ways. Linear dependence and having non-trivial solutions are connected. So the moment you said it's false, it's linearly dependent, that means this is true. It'll have non-trivial solutions. We just have to keep the direction complete in our minds. Think for independence, it means only the trivial solution to AX equals 0. Well, we're nearly done with the set. Oh, there's a bonus one, it turns out. For true or false, the column space of A spans R4, but that's connected with A. It's like the same exact question. Spanning and part A, both parts A here and here are connected. The moment we said part A is false, that means, let's see, the columns of A spanning Rm is also false. Said it really differently, the column space, but that's the same exact concept. The column space of A spanning Rm is just call A equals the span of the columns of A. So that connects directly with that theorem we've been looking at. And it's false just because part A is false as well. Well, we're down to one last one. The dimension of the null space A is 3. How do folks feel about this one? Does this feel true or does it feel false?
True.
I think you said true? Yeah, absolutely. This one comes out definitely true. And the justification on this one is dimension, null space of A. We already saw that it was 3. It was the number of free variables that we detected in the system. So the moment we know number of free variables, we know dimension of the null space, making this one automatically true. Well, again, all this stuff is really kind of intricately connected. Knowing the pivots, knowing the free variables gives you information on spanning, independence, dimensions of a null space. It's all glommed together, which is what makes linear algebra kind of tricky, how these definitions interact like this. But let's move on to the next problem 3. This one's about linear transformations, so it's kind of changing gears a little bit. This is towards the very end of chapter 1 now. We have a transformation that maps R3 into R2. Now, already that tells us one-to-one, it's just purely impossible. You can't take 3-dimensional vector spaces and in a one-to-one correspondence way, squish it down to 2 dimensions. So this one's false, we're expecting, but we'll give a good explanation down here when we get to that spot. Only thing I know about the transformation T is how it maps on E1, E2, E3. But that's a basis for R3. That's the standard order basis. These are just columns of the 3x3 identity matrix. And so there's a theorem all the way back in section 1.9 that tells us standard matrix A of T is formed by just going the mapping applied to the standard order basis vectors, T of E1, T of E2, T of E3 is a really fast way to solve this one. We just take all these vectors, drop them into a matrix as they stand. So 1, 5, 0, 1, negative 2, 0 is that standard matrix A of T. And what we mean by that is specifically, now T of X equals that matrix A times X for all vectors X in the domain R3. We can just analyze A as a matrix multiplication. So it's been a while since we looked into that theorem. Any questions on getting through part A? Okay, so that gives you options now in part B. If you have the standard matrix A of the transformation T, well, you can just calculate what X is. It's a linear combination of basis vectors, E2, 3E2 plus E3. So once you have the vector X, multiply it against this matrix, and you're finding the image under T. But we also know something more. We were told it's linear, and we even found the standard matrix. So we can just use linearity. And this is another cool way to kind of solve this problem. you could say, first, the image of x under t is just saying, in a fancy way, compute t of x. The output, the codomain element, is the image. But now you're doing t of 3e2 plus e3, so I've just substituted in x is that linear combination. But now you can undo the vector addition, or better said, not exactly undoing it, but instead of doing it in the domain, we can do the vector addition here in the codomain R2. Likewise, the scalar multiplication happens in the domain R3, but you don't have to do it there. You can do this in the codomain R2 by just rewriting the scalar multiplication as 3 times t of e2 plus t of e3. That takes us just about where we want to go, because we know the output for t of e2, it's this vector. Likewise, t of e3 is this vector, so we get 3 times 0, 1 plus 1 times negative 2, 0. So altogether, the image of that vector x comes out as negative 2 and a 1. So the work is done right at that step. And multiplying this out, finding out the vector x in R3, just multiplying against the matrix A, it's about the same amount of work, really. So it gives you options on part B once you have that standard matrix. We never actually used it. Well, any questions at all, folks, seeing it this way? Okay, I like going this route because it just reminds us about the properties of linear mappings like these, the way we can do the vector addition, scalar multiplication, the codomain. And last questions are just more concept questions like the ones we've seen before. First one we're being asked is T 1-to-1. Well, addressing 1-to-1 is not too bad because it's tied in with linear independence / dependence with this particular matrix A right here. It has 2 rows but 3 columns, or another way to say it, if you have 3 vectors, but only 2 entries per those 3 vectors, they're automatically linearly dependent. So a lot of ways to think about this one, but you can just say no to the 1-to-1 question because A has at most 2 pivots. If it's a 2x3 matrix, 2 pivots are the most we could ever generate. And 3 columns implies the columns of A are linearly dependent. So turns out independence and dependence, if your transformation is linear, is tied together with 1-to-1 or not 1-to-1. If these were linearly independent columns, we would have said yes, the mapping T defined in this way is 1-to-1, but it's not, it's dependent, so we said not 1-to-1 on this one. And the same kind of idea. 1-to-1 has to deal with columns. But if you're talking about onto, this has to do with rows. And even though we haven't row reduced this matrix, in the one step you would take to row reduce it, you would get a 0 here and a 1 right here. There's automatically a pivot in every row. So let's just say that here. Since A has a pivot in every row, this is connected with being on 2, the pivots among the rows. And if there's a pivot in every row, we can say yes, T is on 2. So we found one image, negative 2, 1. But for every single vector inside R2, it's going to be the image of some vector x in R3. So we've covered the whole space R2. The codomain is exactly the range, is what part D is saying in lots of different ways. Well, we're done with the transformation. Any questions at all, folks? Revisiting that material there? Okay, let's keep on moving forward then. Linear transformation T, so another one of these, is defined in this sideways way. We saw several of these in the textbook, and it's a pretty standard way to write a transformation like this, depending on the context you're working in. Where you know it's linear, they just tell us straight out, so that's kind of comforting information. And we're also told it's invertible. So we want to determine the inverse, T inverse x1, x2, express our answer in the same notation the original mapping was given. That last part isn't worth a lot of credit. If this is, say, a 5-point problem, that last part's 1 point. But it's still important because it's important to just be familiar with the different notations that these mappings can be presented in. So to start this out, I'm actually going to unpack the notation and just write it in the way we're more used to seeing it. So x is going to be x1, x2, but written vertically as a column vector. And then t of x, replacing this with our new notation, is going to be another column vector where entry 1 is 4x1 plus 3x2, and across the comma is entry 2, 2x1 plus 2x2. That's how we're used to seeing it. We're told T is linear, so there's got to be a standard matrix A for the transformation. And that's not too hard to unpack. The vector you see here is a linear combination, which is a result of a matrix times the column vector x1, x2, or just x again. And all you have to do is pull the coefficients. The matrix A is 4, 2, 3, 2. You can imagine this is pretty easy to check. If you take 4, 3, multiply with the corresponding entries x1, x2, in other words, a dot product, you get exactly 4x1 plus 3x2. And likewise for the second row down there. So this is our A, that's our x. We're told that the transformation T is invertible. That means A has to be invertible as well. So this will be a good check on our work. Take determinant A. It comes out as 8 minus 6, positive 2, which is non-zero. And double check the invertible matrix theorem. Non-zero here implies A inverse exists. So that part made sense, that's good. But this isn't just wasted effort verifying one part of the problem. We actually have to compute A inverse to get to this part, determining T inverse. So now compute A inverse as the formula is going to be take the reciprocal of the determinant of A, go back to the matrix A, and it's just a numeric entry game that we do. The entry part is just exchanging the main diagonal. So 4, 2 becomes a 2, 4. The numeric part is you multiply the off diagonal going this way by -1. So we get -2, -3. And so now scaling by a half gives us 1, -1, -1.52. So there's our A inverse. Now we're ready for T inverse. Any questions at all, folks, on the matrix inverse there? Okay, so now inverting the original mapping that was given, it's kind of hard to see how this goes with just doing this from scratch, not using all these tools. But there's another awesome theorem that tells us T inverse is linear as well. That's nice. Along the same lines, T inverse of x is kind of defined in this sort of way, like T was, A times x. It's linear, so it has a standard matrix. And in fact, that standard matrix is A inverse, which is kind of nice. So once we get to here, T inverse of x is just 1, -1, -1.52, x1, x2. You've got the right inverse mapping. We just have to undo this notation, go backwards, and write it in this way. The same notation as the original, mapping was given in. So now we're going to that line. But really, it's not too bad. All we really have to do is say T inverse x1, x2. If you call that just T inverse x, I'm okay with that. It's more about the right-hand side. But this is following the instructions verbatim to the letter. We do the multiplication here and here. So take 1 times x1 minus 1.5 times x2. x1 minus 1.5 x2. Same thing here. We're just multiplying out to the matrix times the vector, but writing the results sideways. So this would be entry 1. Below is entry 2, but sideways this time. Negative x1 plus 2x2. And that's our inverse mapping in the same notation as above. We got it, folks. This one kind of reviews a lot of strange topics and theorems all in one. Any questions on getting through this one here? Okay, let's keep on going through. Next one, this is now in chapter 3, the very end of it, is a Cramer's rule kind of problem. There's one just like this that you should expect on the final exam, where just like on our actual exam, I think this was exam 2, I'm getting a little foggy on when it occurred, we have to use Cramer's rule to get full credit for this problem because it's what the problem is all about. But really, it's kind of a fast problem, just using a few determinants, and we work our way through it. The very first thing, though, is you have to take the system of equations here and write this in as a matrix equation. So that's part of the reason we did all that stuff in chapter 1, write a system of equations as a matrix equation or a vector equation and vice versa, because it becomes relevant down the line. So here's that same equation now as a matrix equation. We rewrite the variables x1, x2 as a column vector here. The right-hand sides is a column vector opposite of equality. And just like what we did on the last problem, we pull coefficients. The projector just went off in the room. Okay, it's back on. Let's hope it makes it through the rest of the day. I guess it's tired. It didn't get turned off from the last class. So pull coefficients from this column, and we get 1, 2, negative 3, 1. So this is the matrix A. This is the vector X. And this is the right-hand side, the column vector B. What we'll solve for is x1, x2. And Cramer's rule is sort of fast for this situation, the 2 by 2 case. First thing we would do for this is compute determinant A. This goes fast. This is just going to be 1 plus 6 for a value of 7. Watch out for the double negatives on that, plus 6. Then after that, we're just solving for x1, x2. We're just about done. We take x1. It's going to be determinant a1b divide by determinant A. So that means the denominator is done. We've got a 7 down there. Determinant a1b, though, we have to be a little bit more mindful of. Subscript 1 is saying take the vector b, highlighted above, drop it into column 1. So 1, negative 2 goes into that position. And then just rewrite the rest of the matrix A. Negative 3, 1. So this is going to be 1 minus 6 in the numerator for a negative 5 sevenths. And we're 1 down. We have our x1. Next, let's solve for x2. Same kind of game, we just change the subscript to a2b. So determinant a2b here. Divide by determinant A. Like before, once we got that denominator, it just gets copied in. Determinant of A2b. Here, following the subscript, column vector B goes into the second column. So 1, negative 2 inside that determinant. From the original matrix A, we plug in 1, 2 here. That means this one's almost done. This is going to be negative 2 minus 2 for a negative 4 sevenths. And at this stage, I would probably call this a decent stopping point, because if you're equation is written like this as a raw system of equations, then this format kind of fits that notation, just saying what individually each of the variables are going to be equal to. The determinant is non-zero, which means this A inverse exists, which means there is a unique solution. And those are the components of that unique solution X. Well, we did it, folks. That's Cramer's rule. It's going to be kind of short and sweet like this because we can do a 3x3 or a 4x4 if we had the time and paper, but it's more just understanding the concept. The 2x2 does that. Any questions before we go off to the next concept? Okay, well, next up, now we're in chapter 4 here. This one looks like a null space. And finding null spaces turns into a really, really common technique after chapter 4. It almost seems like once you find a null space in chapter 4, most of our linear algebra is organized around null spaces. So to determine the null space for this one, not a bad idea to just remind yourself that null A is going to be the set of all vectors x such that AX is a zero vector. So a null space is just the collection of all solutions to the homogeneous equation here. We'll write our answer as a span of a set of vectors, but it's a really fast row reduction. I'm just going to take this, put it into an augmented matrix. 1, -1, 5, -4, 0, 0, 3, -3, augment with a zero vector, and then just start row reducing this thing. So we can add row 1 to row 2 to get started. 1, 5, 0, 3, 0, add that to row 2, eliminating that entry. We get 0, 1, 0, 0, 0. So it's going pretty fast. Now we need to eliminate the entry above that pivot position. So let's copy in that row, 0, 1, 0, 0, 0. Take -1 times this row, add it to the entry above, the row above, and we get 1. I'm not sure if I said -1 or -5. Definitely take -5 though. That'll eliminate the entry above, and we get 1, 0, 0, 3, 0. And this is identified also at the same time, the pivots of the matrix A. That means we have a basis for the column space right at that step as well. So let's write that in. Now this gets kind of tricky. It's not as big of a deal in this problem because the column space of A is a subspace of R2. It's the span of these columns, all with 2 entries. So if I take these vectors in this one weird situation, it is a basis. That's the standard ordered basis. But if this was, say, a vector with 4 rows or 3 rows, and we had just 2 pivots, it actually really matters. You go back to the original matrix A. So just as a safety, a best practice, let's write down a warning on this one for the column space. Always return to the original matrix A. In rare cases like this one, it actually doesn't matter because that did form a basis for the entirety of R2. But in the cases where it's not the entire space R2, coming back here is for safety. So 1, -1, this one is also a basis. 5, -4. And that solves part B, the basis for the column space of A. We still haven't solved part A. That's good to know when you can get the column space. It's just the moment you are in echelon form and you see the pivots. So now back to solving for the null space. Let's rewrite variables x1, x2, x3, x4. We just take these rows, rewrite the system of equations with a careful attention to the free variables. So this implies x1 equals, put in a little space first, -3 x4. X2, well, x2 is just 0. But what about x3? there's not a row for this, but x3 is a free variable, so we'll say it's 1 times x3. And same for x4 as a free variable. x4 equals 1 times x4. So back to this, solving for x. It's going to involve a linear combination using the free variables as the scalars or the parameters in parametric vector form. So once we spotted those free variables, x3, x4, takes us to this step. We come back here, and all we do at this stage is pull coefficients corresponding to those parameters or free variables. The x3 coefficients go 0, 0, 1, 0. That's a pretty big vector, but if there are 4 columns, x has to be an R4 for this null space. So that's why we have such a tall vector there. Likewise for x4, the coefficients went -3, 0, 0, 1, such that x3, x4 are scalars in R. You know, if you stopped right here, I probably would consider this full credit because this is a span. It's just written out in a particular kind of way, showing the linear combination. But usually, if you're following this into the letter, what it really means is just write this. Null A is span 0, 0, 1, 0, comma, -3, 0, 0, 1. But what does that span look like? The span of those two vectors is exactly just this. If you wrote it out in set builder notation, that's what you would write to deconstruct what the span is. So I would take either or. This is, to me, good enough. This is what the main target really was. And it's a good idea to go to this level because if it was an eigenvector problem, you're really exhibiting exactly what the eigenvectors would have been. And this is the eigenspace now. Well, we did it for problem number 7. Any last questions or any comments on this one here? Okay, so I'm not too sure what's coming up next. Let's see, we have something about coordinate vectors and a basis. So this would have been after the null space section. This one is, I think, section 4.4, something like that, coordinate systems. After we defined a basis, we have this interesting information. So 3 vectors, v1, v2, v3, we're told it forms a basis, so we can trust that. You don't have to check it. It's not part of the problem. What we know aside from that is for one particular vector x in R3, the coordinate vector with relative to this basis b is 5, 1, -1. So we want to, kind of like a decoding problem, say what is that vector x if this is its coordinates relative to the basis. Good way to start this problem is just to think of what does this equation really say right here. This whole equation is just shorthand for 5 times v1 plus 1 times v2 plus -1 times v3 equals x. So that's what the coordinate vector relative to this basis, v1, v2, v3, is telling us. So we can decode this, find out what the vector x is, just by doing the linear combination. Take 5 times v1, that's going to be 5, 5, -10. 1 times v2 is going to be just plus 0, 1, 5. The original v2 vector, plus -1 times v3 is going to give us 2, 0, 0. Okay, so it's kind of the fun problem in a certain sense. We just had to know what did this really mean? It's a linear combination. So let's just compute this out. We'll get 7, 6, -5. And then the whole problem is over right at that step. But then the trickier step is the part B next. This one goes backwards. It says, if x is this other random vector, find the coordinate vector of x relative to the basis b. So this is the slightly harder one, but think of it as just two sides to the same process. The first one was like the decoding problem. This is like the encoding problem. This whole statement written in yellow is just saying find x subscript b. This whole thing just is, in words highlighted in yellow, the coordinate vector of x relative to the basis b. But thinking in terms of what this was saying, you can find the coordinate vector just by taking this. It's equal to x1, x2, x3. These are the scalars we're trying to solve for that multiply v1, v2, v3, giving the linear combination. So to get that coordinate vector, we're just solving really x1 times v1 plus x2 times v2 plus x3 times v3 equals this vector x. So that's all this statement is really trying to say. Again, it's just this going backwards, but the backwards process is a little bit more computational. Now we actually have to solve for x1, x2, x3 to get that coordinate vector. We have a vector equation. We can just go now automatically to an augmented matrix. Let's throw in these vectors here. 1, 1, negative 2. 0, 1, 5. Negative 2, 0, 0, augmented with the vector x, which is 1, negative 7, 0. And it's kind of a longer row reduction, this problem this time, because remember we were told v1, v2, v3 forms a basis. That means there's going to be a pivot in every column along the main diagonal, and we need row reduced echelon form, eliminate entries below and above every one of those pivots. So starting here in row 1, 1, 0, negative 2, 1, multiply row 1 by negative 1, add to the row below, and we get 0, 1, 2, negative 8. Now double row 1, add to row 3, replacing it, and we get 0, 5, negative 4, and 2. So column 1 is all set up. Column 2, we need to eliminate the entry below. That means we can copy in rows 1 and 2 to start this next operation. So 0, 1, 2, negative 8 for row 2. And now multiply row 2 by negative 5, adding to row 3, replacing it, and we get 0, 0. So that's negative 14. Positive 40 plus 2 for a 42. This gets kind of sketchy, but turns out that's an even division. So 14 goes into 42 3 times, thankfully. Let's do another row operation. This time, let's divide that row by, say, negative 14. We'll have 0, 0, 1, negative 3. And if you feel like you're getting really good at row operations at this point, you can work on this row, do the operations on these two rows above. But for me, that's when I start to make mistakes, trying to do too much at once. So let me just write it in so I don't mess up the arithmetic on the very last part here. Okay, so now copy in row 3 to start. We're going to multiply by negative 2 on row 3, adding to the row above. So this will become 0, 1, 0. This will be a 6 minus 8 for a negative 2. Then we're going to take double row 3, adding to row 1, replacing it. That gives us 1, 0, 0. So that's negative 6 plus 1 for a negative 5. And then recall, this is x1, x2, x3. So if you read out this augmented matrix to give the system of equations, it's a fast system. x1 is negative 5, x2 is negative 2, x3 is negative 3, and that's precisely what we want to find. That's the coordinate vector, so we can now conclude Therefore, the coordinates of this random vector x that was provided relative to the basis b, that's just asking what are the actual values for the linear combination to make this equation true. And it's these 5, -2, -3. So it's a confusing kind of problem because we have to remember that this is the structure, the idea that starts off all of these. The fact that xb, x subscript b means you're solving for x1, x2, x3. But in either case, how you look at it, it's really just a vector equation. If you can see how to go from here to a vector equation in either case, then it's really not that bad of a problem. Well, that's the entire coordinate vector section pretty much in that one problem. Looks like we're kind of shy on time, so any particular questions at the moment before we take a look into the next? Okay, I'm noticing one problem that we really haven't gone into is a section 4.1 problem. I'll come back to solve the remaining of the problems here, but let's invent one of those section 4.1 problems for our final question on the review. I think that seems about right. This really didn't hit on any of those questions just yet. So let's say a section 4.1 question. I'm not going to ask a whole bunch of really abstract questions from that section on the real final exam, but one question that I'm probably going to go for is something that deals with closure. So let's do a random example. Let H be equal to the set of vectors x, y, such that, and let's just come up with something random here. How about x, y, the product, is bigger than or equal to 0? We could possibly visualize that space if we think about what would this really look like to make that come out as true. But here the instructions are going to be specific. Verify that, let's see, we're going for a closure property. It can be either vector addition or scalar multiplication. Let's say verify that vector addition. Let's say this in a better way. Verify that the closure property for vector addition does not hold using a counter example. So this is the kind of question that I'm going to go for on the real final exam, something kind of along these lines. So it's really testing a lot of different skills. There's the skill of thinking in terms of sets. We're using set builder notation to indicate the subset H of R2. There's also the concept of what is a counterexample in the first place, and the concept of closure. So a counterexample means we need to come up with a particular vector u, another particular vector v, where both uv are in H. And we can determine they're in H by that set membership condition. The product of their entries has to be positive. So we can only start with vectors that came out of the set in the first place. Well, it has to be non-negative. So if I did something like, say, this, that should work. The product of those entries, 0 times 1, is 0. So u does belong to this set. We're trying to break the closure property, so we'll have to eventually calculate u plus v and conclude u plus v is not in H. Because whatever this comes out as, when we multiply the coordinates, this has to flip to negative now, specifically a negative number. So that kind of informs possibly what we would choose here. Anyone see a good choice of entries on the vector u? Yeah, I like that. Let's go -1, 0. If you multiply these two entries, the product of those entries is 0, where x is the first entry, y is the second entry. So this is true. U, v are both in H. Now add them together. U plus v is going to give us a -1, +1. This is no longer in H. We can say u plus v is not in H since -1 times 1 is -1. Well, that doesn't fit. This is strictly less than 0, so we've left the set H. So this proves H is not a vector space. We didn't have to say that part. We were just trying to show the closure property fails. And we did that the moment we showed this right here. We found two vectors that are inside the set H, bona fide elements of that set, but performed the vector addition, and somehow we've leaked out of the set H. That never happens to real vector spaces. This is what closure means. You would have actually still been inside H if this was a bona fide vector space. So expect a question that's pretty similar to that one. If you think all the way back to the homework in section 4.1, there was a couple questions, I think 3 in a row, that was just different scenarios of this kind of problem to take a look into as a refresher. Well, aside from that, we've got about 4 more minutes. Let's see what's coming up next. I think we can do this problem in just about 4 minutes, and then I'll come back and clean up the rest of the notes, fully solve everything. There might be a couple questions like this, where you might have to state a dimension, maybe not too many of them. I think they can be challenging problems, but certain things are just so important that this one actually would make a pretty decent exam question. So in your own words, state the definition of the dimension of a vector space. What I would say to this one is dimension is the number of vectors in a basis. There's more to that. When we went to fully defined dimension, we actually had 3 different scenarios we had to look into. When there is no basis, the trivial subspace containing just the 0 vector, or when our vector space is not spanned by a finite set, when it's infinite dimensional. But when I say just state it in your own words, I'm looking for the main gist. So something really quick. This would be absolutely full credit, even though there's a couple fringe cases here that's not completely encapsulated. So there could be a problem like that, possibly dimension, or maybe some other really fast but important concept. It allows us to address part B, the dimension of P3. We can first say, write down the basis. The standard basis is cursive E or script E, written as 1 t squared t cubed, because P3 is a set of all polynomials of degrees at most 3, so we have to go up to that term there. But since that's a basis and it has 4 terms, we can say dimension P3 equals 4. Or really the shorthand about this is it's always 1 higher than the subscript down below. So you might have some problems where you just have to tell me what the dimension of certain spaces are, like on this one, making it kind of a fast concept question. And for part C, this one's pretty fast as well. Given 4 vectors that span R4, explain why those vectors form a basis. You know, what I would do with this one is just say, let A equal V1, V2, V3, V4. It says the vectors span R4. That means every vector has 4 entries. There's also 4 vectors, so this tells us then A is 4 by 4. That's important because it tells us the invertible matrix theorem is relevant here. So let's pull up that theorem wherever it went. And lo and behold, in the invertible matrix theorem, spanning is logically equivalent to the columns forming a basis. So the moment we know it spans, it's also linearly independent automatically. That's just a different statement up here, linearly independent set. But that's the punchline. It's just a basis as long as it spans. So knowing just spanning with 4 vectors, or just linearly independent with 4 vectors exactly, that's enough to tell you it's a basis. So let's conclude here by the invertible matrix theorem. V1, V2, V3, V4 is a basis for R4. And we did it, folks. That's kind of a faster concept question on this one. There's other things that we didn't quite hit on for lack of time, like say the eigenvalues, eigenvector stuff, diagonalization. At least that was a little bit slightly more recent material that we saw soon. You can always come back here on the notes later on if you want to look into how these problems go. I'll get these solved, fully uploaded. I'll probably be working them on Friday. So after I get caught up on grading homework sets, I'll just move over to finalizing these answers here. Well, we made it to the end, folks. Congratulations on getting through all 15 weeks. Week 16 is just a formality getting through the final. Any last questions at all before we call it a night? Okay, well, have a great weekend, folks. Try not to work too hard. If you are working, I'll be available by email. We won't have class all week. We don't have office hours, but don't hesitate to email me at any time. I'm happy to connect and work with you on anything that might be coming up. But take care. I'll see you all for the final.